Okay. Thank you, Prateek Viman, for allowing me to share my work with everyone at this conference. This meeting is mainly about CGM, hot, cool gas around galaxies, and most of the talks are focused on the more massive galaxies. I think the talk just before mine has mentioned the smaller galaxies and the cool gas. So I'm now going to talk about something even more extreme, and that's void galaxies. And I know this topic sounds a little way out because in this meeting we're talking about starburst and concentrations of galaxies. But I will talk about a really isolated galaxy where we have detected a circumgalactic medium. And I wanted to share this work with us because I think it's important to understand how the smaller galaxies are producing their CGM and what is contributing to the outflow, if there is any, and how they're building their disks. So this talk involves considerable amount of radio work, and so there are several radio people involved: Hui, Dwarka, Preeti, and then Harsha has helped with all the X-ray, and Bhaibhav and Tuhin Ghosh have also I've started some work on Planck data, trying to find the hot gas in voids using Planck data. So I will just mention that at the end. So because it's a little bit extreme, this topic, void galaxies, I will spend a few minutes just describing these galaxies and setting the scenario for what I'm going to talk about, their radio mission, their halos. So I'll first talk about the properties of void galaxies. I'll talk about their cold gas content. And we have heard that in a few talks, but not much. And so I'll talk about the H1 and the molecular gas content of these void galaxies. And then I will focus on the Boötes void. And the Boötes void is extraordinary because it is huge. It's like 60 megaparsecs across. So in our local universe, that is probably the largest empty region in our universe. And I will talk about some galaxies in the Boötes void where we have detected radio halos or extended radio emission at low frequency. Low frequency traces old electrons. So these are tracing hot gas which has decayed, the electrons have decayed, and so we're tracing old extended emission. And then I will talk about the extended emission around one of the galaxies, CG693. Now, voids are huge empty spaces in our universe. I think everybody here knows about the large-scale structure and how galaxies are clustered in walls and filaments in our universe. However, voids have always been somewhat neglected because they are considered empty spaces and that's it. But if you look at the more recent simulations, then you will find that voids also have a considerable amount of filaments. And filaments are very important. Filaments are the roadways along which gas travels, the wind travels in the intergalactic medium. So they are very important for feeding gas onto galaxies, and that's where the CGM connection comes. So this is a simulation, illustrative simulation. On the left you can see a nice cluster, and on the right you can see a void. And if you can notice, the void it's interspersed with a lot of filaments. Maybe not a lot, but a significant amount. And that's important because that means that within a void, you can also have gas accretion onto galaxies. Now, the simulations of recent simulations of the evolution of our universe has shown that when the galaxies evolve and the cosmic web comes into place, then there is a lot of massive star formation, AGN outflows at the nodal points where you get the massive clusters. And from those regions, you will get a lot of outflow. That's the hot gas which will come into the intergalactic medium. Now, this paper also pointed out that in the process, you will also start getting a significant emission of hot gas coming into the voids. So it's as if the voids are surrounded by these walls and have filaments also running through them. And there, from the star formation, massive star formation, radiant activity at the boundaries, you are getting gas leaking into the voids. And this is how they explain the rise of hot gas, ejected material, into the voids, this gray curve here. And the dark matter doesn't change. The void is expanding, and as it's expanding, the sub-voids or the smaller voids get kind of eaten up into the larger void as matter moves away and away from each other. So the dark matter content doesn't really change, but there is a significant increase in the hot gas. So some of the star formation and AGN activity around voids can actually feed hot gas into them. And this is what set us off in this direction of trying to detect the hot gas in voids. Okay, so I will just spend a few minutes on void galaxies. Void galaxies, most people don't know too much about them, but in essence, they are low mass, gas-rich, star-forming galaxies. Now we know from the Dressler relation that only in crowded regions, excuse me, in clusters, you start getting more ellipticals, from mergers, you get more S-zeros. So in the isolated regions, it's not surprising that we have mainly disk galaxies. These disk galaxies are gas-rich. They are forming stars, as you can see. Some of them are quite blue. And also many of them have bulges. Now this is also very important because we know that the AGN will grow with the bulge. And so if these some void galaxies do have active galactic nuclei, then we will also get AGN outflows into voids and not just from the surrounding of voids. Now the masses of these galaxies is fairly low. It's like 10 to the power 8 to 10 to the power 10, few times 10 to the power 9 M-sun. So they are not very massive, which is also not surprising because mergers have not happened here. However, these galaxies, a crucial thing that has played a role in their evolution must be the evolution of the void substructure. Because as the cosmic web evolves, then the smaller voids, they expand and they merge with other voids and you start getting larger voids. So this means that a larger void would have been formed from more subvoids and hence may have more filaments. Because when voids merge, several filaments can be formed. So that's why when you look at several nearby voids, you may find that there are triplets of galaxies and there are several pairs, binary pairs. And there haven't been many surveys, continuum surveys, because the emission here is very weak. And the cosmic web will probably only be able to be observed by SKA because it goes down to micro-Jansky level. However, when you look at it even with H1, you see these kind of filaments collecting galaxies which are very far apart. And this is also another H1 filament. And this is a pair of galaxies which I'll discuss later. And this pair actually, one of them shows a very nice extended X-ray halo. Now, star formation in void galaxies can be quite important, can be several times solar mass per year. This is a very common void galaxy residing in our nearby local void, NGC 6946. It's a bulgeless galaxy. It hasn't grown a bulge, but you can see it has beautiful star formation. So if we put these void galaxies on the color magnitude diagram, you'll find that most of them will lie on the blue cloud. So they are slowly evolving low mass galaxies. So their evolution is actually very similar to the galaxies in the field of clusters, except that it's slower. So I also detected some cold gas in these void galaxies, and they do show a considerable amount of star formation, and some of them are even classified as starburst galaxies. Now the question is that what triggers the star formation in voids? Because usually when you have star formation, either it's triggered by some internal processes like a bar, spiral arms, or there will be galaxy interactions, galaxy mergers. But in a void, in the underdense environment of void, and especially since they are low mass galaxies, we don't see much of those dynamical features. So, and you don't see much of interactions except for pairs and triplets in isolated regions. So what drives their star formation? This is a question that we asked ourselves. And what we think is very important is gas accretion. And this is NGC 6946, which I just showed you. And you can see here that there is a considerable amount of abnormal H1 velocity in this galaxy. And that's true for many galaxies in our local universe, like NGC 2403. A lot of them show actually very extended H1 disks. And the gas accretion is slowly happening and building these disks. So the merging of subvoids has led to the formation of a filament, more filaments in a void than before, and gas along these filaments can lead to star formation and the growth of galaxy disks. It can also lead to the growth of the environment around a galaxy, which can be seen in X-ray, but also can be seen in radio. So one question we asked ourselves, especially after we saw the simulations, was that do the void galaxies themselves contribute to the warm and hot gas that is detected in voids in simulations? Not so much in observations, but in simulations. So we thought about this because if you look at some of the really large voids, like the Bootes void, you'll find that there are several AGN, 5 out of 28 galaxies in the Bootes void host AGN. So it is possible that some of the AGN, some of the hot gas can come from AGN outflows in these inside the void. Can also come from the clusters which are outside the void on the web. So the galaxies within the void also produce outflows, and these outflows will enrich the CGM around it. They'll be connected to the WIM. Along the WIM, you'll also get gas accretion. That gas accretion can also trigger star formation, apart from galaxy interactions, which will happen slowly as the voids merge, subvoids merge. So our aim in this project was to explore diffuse emission in voids. And one of the ways we decided to first look at this is to look for low frequency radio emission. And low frequency because low frequency traces the old electrons, the relic electrons. And this is important, we also thought, as a pilot survey for SKA, because at one stage we will want to study the cosmic web, and finally maybe the cosmic web inside voids. So why the Bootes void? Now the Bootes void in our low redshift universe is probably the largest void. It's 60 megaparsec across, and from what I can make out, it doesn't have more than 30 galaxies, but it's at a redshift of 0.05, and that means that many of the smaller galaxies may not be visible. We may not have been able to detect them. So this is, I want to show this. This circle shows the Bootes void, and it shows you how empty this region is. And you do, however, get galaxies like this. These are fairly isolated galaxies. This is a pair, a galaxy pair. Now, when we started looking at the Bootes void, we compared it with all the other voids that we could see, the local void, which is 20 megaparsec across, and several other smaller voids. And the Bootes void actually has 28 galaxies, of which 4 or 5 have AGN. So that was a good target for us, because when you know that there is an AGN and there is some emission in radio already, it's a good place to start for radio observations. So that's why we targeted Bootes void galaxies. We chose 5 of them, and about 20% of the Bootes void galaxies have Cephers or liners, compared to only 3% of galaxies in the general voids. So that's the reason why we chose Bootes void. Now, another reason why we chose Bootes void is the Bootes void also appears to have more galaxy filaments. And this experiment was done by Elmo, because he has a very good program to do this. And Elmo uses a spines technique, and the Bezos technique to connect at 1 megaparsecs the galaxies, and to hence trace where the galaxies are connected on large scales. So he used this code of his on the Bootes void galaxies, and what we found was that the Bootes void has a significant 39% of the Bootes void galaxies lie on filaments. So this is not surprising in the scenario I mentioned earlier, that Hooch's void or the larger voids have been made up of the merging of the smaller voids. And the merging of the smaller voids would have left behind filaments and walls. So Hooch's void, being the largest void in our local universe, would definitely have more galaxy filaments. So this was good, and this reaffirmed to us that it was a good choice. So the goal of our low frequency radio study with the GMRT was to detect low frequency emission from a sample of 4 galaxies, and then to compare with hot gas. We wanted to see whether there is also X-ray emission, because radio will be tracing the lower temperature gas, whereas X-ray will trace the 10 to the power 6, 10 to the power 7 gas. And so let me quickly go on to the observations. So the observations were done 2-3 years ago, and we got 14 hours of time for these galaxies. This was not done with the upgraded GMRT. So we were not. We had some more time on the GMRT, but so we didn't get the updated. So it wasn't as sensitive, and maybe we could repeat this later on. But these, let me just discuss our results now. These are the 4 galaxies, and this is the galaxy pair, and you can see that the redshift is pretty high, 0.04. For continuum for optical, a Z of 0.04 or 0.05 is not much. But when you go into radio, anything beyond Z is equals to 0.5 takes several hours of observations. Okay, so now since I'm running short of time, let me just show you the extended emission. This is Markarian 845. This is 235 megahertz and 610. Then this one is 1428. And this one, Zwicky 81, which lies on a filament, has very extended emission at low frequencies. And then let me show you the interacting galaxy. So this pair of interacting galaxies is interesting because this galaxy is a starburst galaxy. It shows enormous amount of star formation. And this galaxy is a Seyfert 1 type galaxy. So this has extended emission, has very limited extended emission, whereas the other galaxy has a lot of emission. And if you compare it with the optical is maybe not even half the size of the radio extent here. And so the spectral index, when you calculate that, then you find that CG692 has a very steep spectral index, which indicates star formation. Okay, I'll skip that. So the X-ray emission. Now, X-ray emission around void galaxies is difficult because not many have got targeted observations. Several of them have been detected with ROSAT, but follow-up deeper observations with Chandra or with XMM are very few. And so we're investigating that. But let me share the one case where we have a nice emission. So this is CG693, and we've detected a nice extended emission of X-ray gas around this galaxy. It was only about 18.8 kilosecond, and the whole extent of this emission is about 50 kiloparsecs. The galaxy itself is about 20 kiloparsecs. So when you look at the optical spectra shows really nice broad emission in CG693, which is the one here showing the X-ray emission. The one which shows nice extended radio emission is this one here and has a nice sharply peaked star formation emission line. And the star formation rate is very small for 693, but it's quite large for 692. Now the Chandra X-ray emission, I just wanted to show you how the contours look again. If we smooth it, it looks a bit extended in this direction. And this direction is not lying along the spiral arms, which you can see in the previous emission here. So one thing I think we might be seeing an outflow in this direction, but we don't have enough sensitivity to really say anything for sure. There are no emission lines in this galaxy, And so we have used the optical emission to find out the black hole mass, which is a few times 10 to the power 7. And this is an overlay of the X-ray emission, which is very large, much larger than the radio emission, both at 610 and at 235. So there is a clear distinction between the X-ray contours here and the radio contours. They don't look as if they're affecting each other. Now I just wanted to mention another galaxy which we have found, that is Chandra Data, Markarian 202. It's also fairly isolated, but not in the Bootes void. There is maybe some emission lines also in the spectrum. And before I end, let me just end on this note that we have been looking for hot diffuse gas in this void, and we've looked and found some X-ray. We found radio emission halos, not around a lot of them, but at least around maybe 20% of galaxies around the Bootes void. Now, one way to actually quantify the hot gas or whether there is warm gas in voids is to look at the Planck data, stacked data. So that's something that I started doing with a student here, a NICER student. And what he's done is, unlike the other Planck studies where they have been stacking the voids, one on top of each other. What we are doing is we are using the void galaxies. And so we are taking the void galaxy and we are stacking the emission in their TSZ maps. So the hope is that if we get a lot of galaxies, and we are still doing it, we may able to see something like the CGM that is seen around the red galaxies in the Planck data. So Bhargav has got some preliminary result, but that's only 128 galaxies. However, one thing we did find very strange was when we did the radial profile for Bootes galaxies, which were 28 galaxies, we find a lower temperature. And so this really shows that it depends upon the void size. So if you have a very massive void, it may be very cold. But if you have a smaller void and you're having a lot of feeding into that void, you may have a fairly warm void intergalactic medium. And I think this is very interesting because it shows that it's not exactly like a black box. You can't say that the voids will be taking all the missing mass that you want to see in the universe. So I think it will depend a lot on the void size, which can't be quantified also because voids have very strange shapes and are all interconnected. So I think Planck data will be the way to go. So I'll stop here.
Very nice work. Just a quick question: what does the X-ray spectrum look like when you find the detection? Is it thermal or temperature?
Oh, temperature was 10 to power 6 something, 2 times 10 to power 6, I think. She actually fitted the log curve. We didn't find any emission lines. I will look it up and tell you.
So the hit rate, is it that there's just not any data other than the one you showed, or
yeah,
because it's
there's no data.
black moon, it's not detected?
No, I think there's no data. Very few galaxies have been detected. Because RUSAT was it was a small sky survey, but it's a very shallow, and many of them which have been detected later in Chandra do not show up in RUSAT. So it's just that they don't have data.
So this extended X-ray emission, which doesn't match with the radio. So how will you explain that?
That's coming from the AGN, and because it's got a CFIP1 nucleus, so it's being fed by the AGN. Whereas the companion galaxy, it doesn't have an AGN, it has only star formation, very narrow emission line, so it's being fed by stars.
That's the other end. That's